In this section of chapter 4, I'm going to discuss Markovnikov's addition reaction to alkenes. Alkynes also give similar reaction. So if you understand Markovnikov's reaction involving alkenes, you can also predict products of reaction with alkynes, which would be discussed in a different section. Now first we are going to remind you about alkene. Alkene must have a double bond like this. Now on paper, both the bonds look the same. Just like in triple bond or alkyne, all the three bonds look the same. But in reality, as we discussed before, one of them is the sigma bond, which is a stronger bond, and the other one is the weaker bond, which is the pi bond. In alkyne, on the other hand, one is the sigma bond, and the other two are the pi bonds and the weaker bonds. Here I'm showing you addition reaction involving HCl and an alkene. You need to focus on the carbon-carbon double bond and then focus on the carbon containing the double bond that has the largest number of hydrogen. So in this case, this is the carbon that has the largest number of hydrogen. Markovnikov predicted that hydrogen of HCl, HBr, or HI would go to that carbon that already has larger number of hydrogen. So obviously, this hydrogen would go to that carbon, and Cl would go to the other carbon. So let me put down dotted lines. Cl would go to the other carbon, and then finally you end up with this product. So here we mention here, H goes to the carbon with larger number of hydrogen atoms, just like money goes to a person who has more money. So hydrogen we are comparing with money in case of a double bonded carbon. Even though I have shown you here one reaction, but almost in every case, Markovnikov's rule is applied, even for alkyne. Now here we are showing you the mechanism that why Markovnikov is right in predicting the products. Scientists understand it better these days. So here in the double bond, one of these is a pi bond, and we're showing an arrow. Arrow means here you have a pair of electrons in this pi bond, and it donates that pair of that electron. This is a loose bond that we all know. The pi bond is the weaker one, and that donates to the hydrogen. Now why hydrogen would be attractive? Because Cl is more electronegative. It is coming from right hand side of periodic table. If you look at a periodic table, hydrogen is from far left and Cl is towards the end, right end. So this is delta plus and Cl gets delta minus because delta has larger electronegativity. So obviously electron pair coming from the double bond, it'd be attracted towards delta plus that has a small positive charge. And as a result of this, whenever this pair of electron goes to H cannot hold on to two bonds because pair makes one new bond, and then it already has a bond here. It has to give up its bond with Cl. And that's indeed what happens, that Cl gets out. And that's what we are showing you with this black arrow. So Cl leaves with pair of electrons so that the new bond can be formed, and that's how this changes to CH3, and you can see here CH3. Now the question is, how do I know that this carbon has plus? Again, this is a formal charge. Each bond represents a pair of electrons, and it would get a half share. So this carbon would be getting share of 3 electrons from 3 bonds. And valence electron for carbon is 4. If you look at periodic table and count from far left along that line until you reach carbon, you'll find that carbon has 4 valence electrons. So it's supposed to have 4 valence electrons, but in sharing it has 3. So 3 electrons present. So that means from 4, because of sharing it got 3, so it lost 1, and that's why it has a plus. This is one way of looking at it. And the other way, you can also see that since CH2 and this double bond is contributing electron, obviously is losing the share of its electron pair. The next step, this is Cl minus, by the way. Again, the same way we can find out these charges. We count electrons. It has 8 electrons, and neutral Cl is supposed to have 7. Again, that's the valence electrons. So 7 valence electrons, but in this case it has 8. So it has an extra electron, and that makes it negative. Now that negative would be attracted towards positive, which is carbocation, which is formed in previous step, and that's why we are showing you an arrow. So arrowhead is always from electron pair to a positive center. Either it's a +1 or it could be just delta plus. So in this case, you see this black arrow heading towards carbocation, and that's how you get this product. Now the question is, why hydrogen is bonded to this end, why not the other end? This has to do with the stability of the intermediate carbocation, because this forms 3-degree carbocation. In case you didn't remember, 3-degree means this carbon is bonded to 3 other carbon, and you can see that this is 1 carbon, this is 2nd carbon, this is 3rd carbon. So 3-degree carbocation is more stable than 2-degree, and 2-degree carbocation is more stable than 1 degree. So keep this in mind, since 3-degree carbocation is formed in this case, and that's favored. Nature always favors whatever is more stable. Since this carbocation is more stable, so it's going to exist in large abundance, and that would end up in this product. So we can now explain the basis of the mechanism, Markovnikov's addition reaction. Now let's go over one homework problem, which is on page 117, 4.3, and let me do both A and B, and so that you have an idea about carbocation. The question is, show the structures of the carbocation intermediates you'd expect in the following reactions. So I'm just going to leave out hydrogen, except when the hydrogen is with the double bond, because then for our understanding we're going to need it. So CC, this is part A, CC, C, then you have CH3, and then you have a double bond, and then you have C, H. As I said, I'm going to write down hydrogen when it's with the double bonded carbon, then C, C, C. Let me double check whether I copied everything right. Okay, there are 1, 2, 3, 4, 5, 6. So I have 6 in the longest chain, and there are 2 methyl groups. One in the 3rd location, the other one is in the 5th location from the left. Okay, now you are adding HBr, so you're going to add HBr. Now keep this in mind. Quick way to get the answer would be go by the Markovnikov's rule. So hydrogen would go to that carbon that already has larger number of hydrogen. So obviously this carbon already has 1, the other carbon doesn't have any. I'm focusing on this carbon-carbon double bond. So obviously the first hydrogen would go there, go to this carbon with asterisk. As that hydrogen goes there, the double bond would be broken, and this would result in 3 bonds around this carbon, and that carbon gets the positive charge. So this is the carbocation you're going to get. Let me now write down more clearly. C, 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 C plus, and then you have C, H, H, C, C, C. So this is the carbocation you're going to get for part A. And what kind of carbocation is this? This carbon is bonded to 1, 2, 3 other carbons. So it's a 3-degree carbocation. Even though they didn't ask for, but I did it anyway. Now let's go over part B. Part B has a ring structure, which is pentagonal ring. So let me draw that. 1, 2, 3, 4, 5. That's the pentagonal ring. We have a double bond here, and then CH, CH3. CH, and then C. Again, I left out all the hydrogens. Now HI, and you are adding HI this time. Again, hydrogen would go to this carbon with the double bond. Let's highlight that. This carbon, I'm showing with an arrow, this carbon has hydrogen. Other carbon doesn't have any hydrogen. This is the other carbon of the ring. So obviously the hydrogen would go here, and let's attach the hydrogen there. So this is going to be the point of attachment of hydrogen. I'm showing with dotted line. So this would give me 5. Now this is part of the ring. Then I would have CH, H, and then I have C here. Again, this carbon has positive because it has 3 bonds. So this is the carbocation in part B. Now, what kind of carbocation is this? Let's examine that by drawing this carbon at the center. So this carbon is also bonded to 3 other carbons. So it's also 3-degree carbocation. Now the addition of water also happens exactly the same manner. So in other words, instead of water, we can think of water as H plus and OH minus. So this would be H plus and OH minus if you write down side by side. So that makes H2O. Now focus on these double bonded, and this carbon on the right with the double bond has 1 hydrogen, but the other carbon doesn't have any hydrogen. So obviously the first hydrogen would go to this carbon. So let me dotted line, I'm showing you the hydrogen, and that's going to make a carbocation in the next carbon. So let me show you that. 1, 2, this is the 3rd carbon, and that gets the positive charge or carbocation, and then this would have now additional hydrogen, so obviously it becomes CH2 now. CH2, CH2, CH3. Now in next step, OH would get bonded, so OH minus would get bonded. I don't have to show the mechanism unless they ask you the mechanism. You can just quickly write down the product, which is this. C, 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 OH, then CH2. I don't have a space here, so make sure you have that CH2, CH2, CH3. So this is the final product you're getting, and you can write down in just one step. Hydrogen going to the carbon with larger number of hydrogen, or 1 hydrogen, the other, and OH goes to the other carbon. But in case they ask you to write down the mechanism, then write down this carbocation in the middle, which is an intermediate, which finally gives the product. Here the mechanism is shown. With H2O. First, we can see this H plus is coming from the acid. So electron pair is coming from the double bond, and that forms a bond between carbon and hydrogen, and this is the new bond they're showing you. And obviously that gives 3 bonds to the adjacent, the next carbon, which originally had a double bond, and that's the carbocation. And H2O has oxygen with pairs of electrons, 2 pairs of electrons, and that gets attracted to that positive. And so that's why this is why H2O gets attracted to positively charged carbon with this electron pair on oxygen. And so this is the new bond formation you can see here. And why this is positive charge, you can again count the electron around this oxygen. Two electrons are solely on oxygen. Then there are 3 shared. So it'd be 2, 3, 4, 5. Those 3 are coming from the bonded atoms. So altogether, oxygen has 5 electrons. But if you look at valence electrons, oxygen has 6 valence electrons. But in sharing, it got 5. So it lost 1, and that's why there is a positive charge on oxygen. So always try to understand it this way. That way, you'd find organic chemistry quite interesting. So it's basically the same thing I'm showing you with the periodic table in front so that you can understand these positive charges. Remember, just a few minutes ago I said that oxygen would have 6 valence electrons. So this is oxygen. So you can count from line 2, beginning of line 2. 1, 2, 3, 4, 5, 6. So that checks out. Now these are additional reactions. So you don't need to really memorize these reactions. In exam, we'll mostly give you the most common ones like reaction with HCl, HBr, HI, H2O. Of course, these are, sometimes you see catalysts too. So like in this case, you don't need to worry about other stuff which are catalysts or helps in the reaction. The key thing is addition of H2O in this case as H and OH. So H goes in here because that's the double bond with hydrogen. The other carbon doesn't have any hydrogen. So obviously that gets OH.